Okay, welcome back everyone to the undergraduate seminar. It's a pleasure to have you here today. We've got Ben Chislett, who's going to talk to us about ray tracing and the light transport equation. I know Ben has read up a lot on ray tracing, and I'm very excited to hear what he has to say for us today. So thank you for coming and speaking. Thank you for being here. We look forward to hearing what you have to say.
Thanks for having me. All right, seeing a lot of friends in the chat. That's great. So let's get into it. So there's not really much in terms of scope for this talk, just a lot of concepts to cover. So first off, I'm going to talk about what exactly we're working towards. Specifically, we want realistic images and not just pretty images. Then I'm going to talk about the what. This is the model and the framework that allows us to be sure that as long as we satisfy these mathematical constraints, we'll be developing something that truly models reality. And then within that framework, we're going to be exploring some techniques to come up with solutions to the light transport equation, which in other words are pictures. And so we can use those to generate realistic images. And we'll talk about some of the techniques. Full screen is not a bad idea. Better?
Yeah, that looks great.
Okay. And then we'll talk about some of the techniques we use to speed this up, make this more efficient, and bring it to real time if we have time for that. So without further ado, we want realistic images. Slide number 1. So I think the why is pretty obvious. CGI in films. CGI is kind of used as like a catch-all for anything that they insert that isn't real physical objects. And then in that instance, they really do want it to be as believable as possible. And they'll go to great lengths, having actors wear those green suits with the dots all over them, measuring the lighting and everything to get it just right, because otherwise we tend to notice pretty easily. Also realistic animation, so that's animation that tries to model the real world. And even some films can benefit in terms of visual quality from realistic effects instead of traditional pipelining. And then of course video games. Just about every major video game these days is going for realistic graphics, and bringing that to real time has a whole other host of problems. So we're first going to talk about how. So what do we actually need to do to make these realistic images, and then how we can make it efficient. So this is the diagram that might not make any sense yet, lots of symbols and arrows and stuff, but I'm hoping that we'll get to a point where this sort of makes sense. We can say, yep, this is how light works. So we'll start from the beginning. We want to build a model of how things look. And that's kind of tricky because you can say, okay, well, we know that there's light, and light kind of exists. It comes out of these things we call lights. But how does it work? So really, we say the light transport equation. And what we mean by that is that light is actually moving around. And as sort of a counterpoint, we can talk about this naive model where we say, okay, let's just paint everything. Let's say every point in space has a color. And then to generate an image, you just take all the set of points that you can see. You take their color and you put that onto the image. And what you get is something like this. So there's no shading, there's no lighting, there's no gradients, because everything has a color and it's fixed, right? If grass is green, then all grass are the same green. And it turns out that that's not really how things are. So there's a small caveat I'll tack on here, say emittance. Things like light sources don't have an inherent color, they give off light. So we'll add this term into our model here, LE for the emittance. So that's light that comes out of a thing. And then we add perspective, and this is where things really get interesting. So I added in this other term here, omega O. This is for the light that comes out of a point. So I'm going to have to start drawing, otherwise things are going to get pretty abstract pretty quickly. So let's say we have an eye, and we are looking at a whole bunch of things in some span, but I'll focus on one point in particular, right? And so at some point in space, we're going to call it X. It depends, in fact, on where you're looking from, that what you see. To be convinced of this, think, for example, of a mirror. So depending on where you're standing, you'll see something different. And that sort of motivates another change, and says that we still aren't even enough, even with this extra term, right? So this helps, and we can say we can sort of model that the color of a thing changes depending on where you're looking from. But in fact, in the case of this mirror, a term is not sufficient, right? It's not to say that a mirror has a color based on where you're looking from, because it doesn't really have a color. It's not fixed. It depends on the world around it. It's really just reflecting something else. And what it's reflecting is actually the light that comes in from somewhere else. And this is where things get kind of tricky. So hold on to your papers. We're going to switch from a function to an integral. And now this is going to be really weird because we just manifested this integral into existence, right? And there's a lot of weird stuff going on. So this Li term is for light in. So now our light model says the light out at a point at an angle is equal to the light emitted at that point at that angle plus all of the light coming in. So this domain omega is going to be basically the half sphere or sometimes the full sphere if we're dealing with glass of all of the light that's coming into a point, right? And then the differential here is going to be in terms of one of these omega i's. This is the light coming in, right? So we're basically summing up all of the light that comes in, and then we're saying it's going to come out, and that's what we're going to see. So now we've got another model, but we lost the color, right? We say, okay, well, you sum up all the light that comes in at that point, at every angle coming in, but we lost the fact that things look differently, right? So we're now transporting light. We now have a model that says light moves around and this is how, but no longer are we sort of accumulating light along paths because everything looks the same. So where did that F term go is the big question here, right? How do we incorporate the fact that things have color? Some things absorb a little bit of light, and the light that leaves them is in fact what determines how they look like. So what we're going to do is we're going to repurpose our friend F into what we call the scattering distribution function. And this can look kind of weird at first glance. So it's now an extra term into our big light model that takes the in and the out. So this is a function that says, here's how much of the light coming in gets scattered to the direction that we're looking from. So I think I might have a picture. Here we go. Okay, so this is a very generic scattering distribution function, and it encompasses a whole lot of stuff. But in the simple case, it might just have one of these behaviors. So say the light comes in, it hits the surface, and then it comes out. And how we would map that to our function is we would say that we still call it f, and at that point this would be x, and then out and in would be specifically coming out and going in. We would say that here is equal to 1, right? And what that means is that all of the light is concentrated precisely in one direction, and it's 0 elsewhere. Right, so this means that if you evaluate it with some other output, it would give you nothing, 0. So no light is coming out. And what this models is actually a mirror, right? So in a mirror, you have exactly one ray in and exactly one ray out, and everywhere else, no light is reflected. So it's not to say that if you were standing over here and you were trying to look in some other direction, that you wouldn't see anything, but rather that you wouldn't see anything from this direction. And that sort of encompasses the notion of perspective, in that if you're standing somewhere else, what you see is nothing from over here. You can't see around corners in that way. What you see is in fact only this ray coming in from that same angle that you're looking at. Okay, and now our model was not completely correct. So previously we were building up things that were correct in their own systems, but missing some terms. But now we had something where the system is complete, but we're missing some term for correctness. And we call this term the cosine term, and it's a weakening factor that we add into this integral to account for some properties of that integral that we didn't quite talk about. And this is always very tricky, and I have still yet to see a good explanation of this. So I'm going to wave my hand a little bit and hope that we're all okay with its existence. So what we're saying is that basically the proportion of light that comes in from a shallow angle is not equal to the proportion of light that comes in from a steep angle. And that's precisely because the amount of solid angle, and that's the 3D equivalent of radians, basically. So the surface area, the relative surface area on that sphere actually varies with the angle at which you look at it. And it varies precisely by this amount given by cosine of theta I. Now, what is theta I? It's actually just the angle corresponding to omega I. And in practice, we calculate this as a dot product. So you'll remember from first year linear algebra that you can actually express this as the dot product of that vector and the normal just being the surface normal of the plane that that lies in. Okay, I've spoken a lot of words. How are we feeling? So right now we have most of a light model, and this is the sort of thing that you'll see in some textbooks, right? They'll say this is the light model. Now I'm going to tack on some more terms, but okay, so far so good. I'll take that. All right. Can we do a recap? Okay, I'll add a few more terms and then we'll do a recap. So I'm going to sneak these guys in. So the first thing is going to be color. What I mean by that is, what are the units of LO? And if the answer to that is a scalar, then what we're actually generating are grayscale images. Because if at every point for every angle, you can only generate one scalar value, you don't really have that RGB color that our monitors are used to displaying. And so to expand this to be more general, we're going to add in this lambda term that accounts for the wavelength of light. And so in most applications, what you'll do is you'll take queries now for every point that you can see, give them the direction that you're looking from, and you'll also take 3 specific values of this wavelength, one for the red, green, and blue channels. But if you're really trying to be particular, if you're trying to capture some complex aspects, you can simulate with more and more different wavelengths and accumulate that up, and you might even be able to see something different on your RGB monitors. So this is more for long form than real time, but sometimes it is beneficial to check with a whole bunch of different wavelengths. And then the other term is going to be time. So I call it motion here, but it really captures a lot of effects. And it says that things don't look the same at every time. And that's kind of obvious, but it's important to build this into our model because anytime we make a claim like this, we say the light at some point and at some angle is equal to some quantity. We need to make sure that that holds true for every other parameter that we're inherently holding fixed, or at least leaving out of our model. So if you're doing something like animation, it wouldn't be sufficient to say that the light out at a point and an angle is equal to some quantity because it changes over time. Maybe the perspective moves, or more importantly, maybe the lights turn on and off. Maybe the lights disappear entirely or they move around. All of these are captured by parameterizing our system in terms of time. And that's really just a small difference. It doesn't make any practical effect on the computations that you're going to make. But it's important in formalizing our system. Okay, and so I'm going to stop there.
River had this
this
question about a recap.
Yes, yeah, here we are. Okay, so to recap, this is the light transport equation. This big guy that captures all this behavior. So we started out, we said we want to build a model of how light works. And my claim to you is that this is the model of how light works. So there are a few caveats, things that don't quite fit into the system, but by and large, for generating realistic imagery, this models how light works. So if I'm sitting here at my computer and I'm looking at a screen, and that screen is emitting light and is telling me what to see, it's displaying me this information on the Zoom call, that's given by this term here. That says that for each point X on my monitor, and for each angle that I'm looking from, it's emitting certain wavelengths of light, 3 of them in particular, red, green, and blue. And at every time, it might be changing as I'm drawing here. The light that I'm seeing is changing. And then we've got this other thing, this big integral that captures all of the light that comes in and gets bounced around. So what happens is, let's say my light is on in this room, right? So let's say we've got a light that's shining. And what happens is that light comes out of this light, I guess, a bit of a conflict in our nomenclature. But light is emitted, right? And it comes in and hits my monitor. And then a tiny amount, the proportion of which is determined by this function here, It says that a tiny amount of that light actually bounces off of the monitor and into my eye. And so I see that as well. And this integral captures that from every possible direction that light could be coming from. And you might say, well, what's the source of this light? But it could really just be light bouncing twice, right? Say the light comes off of my ceiling light, hits my ceiling, hits my monitor, and then goes into my eye. Now, would that be a lot of light? No, definitely not. But assume for a moment that my monitor is turned off, right? It's not emitting any light. I still see something, right? And it's not just a pure black void. There's a little bit of reflection. There's some glare. I can sort of see that even though it's turned off, this is a computer monitor. I can recognize that. The reason for that, it's being illuminated from elsewhere. And that elsewhere is all the light coming in. And specifically, it's mostly light coming in from this direction. So that's that cosine term. It says that light that would be coming in at a direct angle is more impactful than light that's kind of glancing by. And that's our light model.
So just to make sure, I guess you're saying that ray tracing is basically light goes bouncy, bouncy, and then you get color?
Yes, mostly. So I haven't I haven't introduced ray tracing yet. This is simply from a mathematical perspective, trying to lay the foundations. Let's say we're building a system that if we can satisfy it, then we can generate images, right? So this is more physics and math than it is computer science. We haven't introduced the notion of tracing rays or generating images. All we're saying is we're developing some system in which you can query, right? You can say, what's the light at some point? And then to generate images, you just take some plane that you want to capture, that's your image. You say, I'm gonna pretend there's an eye here, and I'm gonna look through that plane, and all of the points that you hit, you can query this light model. You can say, okay, so what does that point look like if I'm looking from here through this plane? And that will generate you an image. And that is where ray tracing begins. But we'll get into that. Okay, I think I got a notification that someone raised their hand. We'll take a pause for questions.
I had a question. Where in this model do you see things that are transparent? Specifically things like refraction or lenses?
Right.
That in this model, is that part of F or?
Yes, so let's go back a few slides. So the scattering distribution function is a very general term, right? So lenses would account for something like this, the transmission, right? So when it travels through a surface, like a lens or glass, it comes through and it's scattered at a different angle. And so in slightly modifying our system, we can say that if we consider omega to be a full sphere instead of a half sphere, then the surface we lie on no longer needs to be transparent. And so you can take this function, you can say, okay, well, in fact, maybe no light is bounced off, right? In the case of a perfect window, right? No light is actually reflected, and only it passes through, right? And so in that case, you'd only be looking at the other hemisphere.
All right. And refraction would be modeled by the interaction between omega 0 and omega I somehow?
Yes. Yeah, and we can actually encode something like Snell's law as a relation between the angles of theta I and what would be theta O.
All right, thank you.
Great. Okay, so I use some language here. I say we'll leave it to the engineers. What I mean by that is that traditionally in graphics, we don't start by building a model. In fact, this light transport model didn't come until 1986, long after we had been trying to generate images. So what had happened before that is we had some constraints of a system. We have these hardwares, this amount of memory, and we're capable of generating these artifacts, right? If you have a digital artist that's only capable of building a mesh from triangles, right? That you can really only model triangles. And so the images that you can generate are restricted by that. And so what they would do in the past is that they would take the technology, the hardware, and the ideas that are available at that moment. And from it, they would try to generate the best images that they can. Here I'm taking the inverse approach. I'm saying, here's how light works. And inside that system, we're going to try to simulate it. And if it happens to be really slow, if it takes too long, that's okay, because we know that that's going to be a realistic image. And then all we need to do is find some other way of generating that same realistic image faster, but inside that same framework. So you can sort of implement, I don't want to say hacks, because hacks is a bad word, but sort of like tricks that you can use, things that don't quite fit into the system, but still enable you to capture some of these effects, right? So for example, some magnetic effects at very high velocities or for very high magnetic fields, you can have some interplay between the magnetics and the light itself. So the light might be bent, and a bending a ray is not really in this system, right? You'll notice that these rays sort of have to be constant. By definition, you know, they have to have that same angle. But if they're instead arcing around, things can change. But you can apply, let's say, like a simple post-processing step, right? If you're trying to render a black hole that exists somewhere, and you know that light sort of bends around it, maybe you can't render that within your framework, but what you can do is you can sort of shine a light from the beginning to the end, and then you can add some glow afterwards onto your resulting image, and that'll accomplish something that looks the same, even though you haven't built it into your system. So that's what I mean when I say that we can leave these effects to the engineers. Okay. So part 2, evaluating the light transporting equation. So this is where we step into the domain of ray tracing. This is now how do we go from that model of how light works into actually building images, right, from the ground up. So what we want to do is we want to evaluate that integral. So I'll go back a few slides. This guy here is the problem, right? So in actually putting this into practice, querying points and angles is pretty trivial, right? You can develop a whole bunch of different camera models, but no matter which one you do, you're going to have to query points and then turn them into an image. That part is more or less solved. It doesn't take too long. We can do it pretty easily. So if we didn't have an integral here and we could just evaluate a function, we'd be set and we'd be generating real-time pretty images. The problem is that we've got an integral here. Now it's not that we're doing an integral over a sphere, because that's doable. The problem is that f is a function, right? And li is a function, and neither of these are simple, right? So in the case of a mirror, perhaps, we have that f is exactly equal to some Dirac delta function, which basically means it's 0 everywhere except for one place. And that's easy to simulate analytically. But what if it's not? What if it's like brushed metal, where it mostly goes in one direction, but in fact, it kind of scatters a little bit. And also maybe it scatters backwards too, because of some grooves in the metal. And representing this mathematically would be trivial, and we do have models for that, but it turns out that integrating them, not at all easy. And to make it even harder, it's a product of terms. So this term, the light in, is also not trivial, and we almost frame this recursively, right? Because we say, well, the light in at some point is really the light out at every other point, right? So let's say we've got a box, and inside that box, at the top is a light, and at the bottom is a cube. This is called the Cornell box, and it's a common, I guess, test bed in graphics. And a long time ago, one guy named Cornell, or at Cornell University, can't remember if it was a person named that or named after the university itself. Once upon a time, someone built a box, a physical box. They painted the walls, and they took images of it, and then they tried their best to render that and use that as a test to see how close they would get. And what they found is that you can apply these light models to something like this box. Thanks for the link. So it turns out that, let's say you're building an image, right? And you're querying this point here on the back wall. And in doing that query, you're trying to evaluate this integral. Thanks. So you'll say, okay, take all the light that comes in. And it turns out that all the light that coming in is the light that comes out of this light, right? So this is a light source. So obviously all the points on this light are going to be relevant. But also you get some scattering from the wall, right? So the light that comes and bounces out of the light onto the wall and then onto your point is still going to contribute. And so in sort of that framework, you can phrase this problem as the light coming in at some point is equal to the light coming in at some other point, right? And you get this expansion of the integral where you're doing ray tracing in terms of ray tracing, right? You're bouncing rays all the way around the scene until either they don't have any light left in them, or they escape off to infinity. They kind of fly out into outer space and they can't interact with anything anymore. In either case, my point is that evaluating this integral is very hard, right? It's a big nasty product. We don't even know what it might be. So we can't use analytical methods, right? We can't solve it directly. Furthermore, we can't solve it automatically, right? So if I were a digital artist and I were adding constantly new things into the scene, these integrals that are everywhere at every point and every angle would be constantly changing. And so there's no way, even if you did sit down for weeks and weeks trying to evaluate this for some scene, any tiny change would completely upend that process. So what we need to do is we need to turn to statistics, and we do estimations. We say, okay, if I can't solve it directly, yeah, all scenes are dynamic. Things move, things change, things get broken, exploded, deleted. Right, so we want to do it fast, and in order to do it fast, we need to approximate it. So what we're going to do is we're going to use Monte Carlo integration. And that's named not exactly after the gambling, but rather after the randomness, the chance. So what we're saying is we're going to say we have some function big F. And that function is going to be precisely all of the terms from our previous function. So now we're just going to say this is a general technique of evaluating an integral when you don't know how to do it directly. So what you're going to do is you're going to say, okay, well, this V term is simply just the volume. So that's whatever the integral would be of the space with nothing else. And that's trivially calculable because we're just doing an integral over a sphere. And so the volume of a unit sphere is known. And then you're going to say, I'm going to take n samples, and I'm going to choose xi's. So now you see we no longer have x dx, but rather we're just taking samples. Where are we taking samples from? Well, we're taking samples from the unit sphere around that point. Right? So what we're doing is we're saying, okay, well, what about this guy? Anything over there? What about over here? And you're constantly just sampling inputs into this function. And the sampling usually is done in terms of light coming in because that's the parameter for our equation. And so you're sampling these light inputs and you're adding them all up and then you're taking the average. And what happens is that as n goes to infinity, this converges to our integral. So great, all we need to do is a million, not even a million, but an infinite number of computations, and then we'll be set. Well, that's no good either, but we're getting somewhere. All right, so Monte-Color ray tracing, putting this into practice. What we're going to do is we're going to take samples from our integral until the output at some point, at some angle, converges. What I mean by converges is that in taking samples and averaging them all up, eventually we're going to get closer and closer to what the real value is. And so eventually, after taking millions or maybe billions of samples, you're not going to be adding any change, right? And so eventually, it's going to be stable. It's going to converge. You can prove that mathematically, but it's known. And so when it does, or when it's sufficiently converged, then we just stop taking samples and you ship the image. So now, how do we evaluate Li? Right, that's the only open problem we have left to building images. Right, so you'll notice that now instead of integrating f, we're evaluating it. Now evaluating little f is no problem, that's just our scattering function. And we know for every material how light scatters. We're just building that into our material model. But in terms of Li, things are a bit trickier because we've got to say, okay, well, we've got to evaluate it recursively, right? You've got to not only trace the first ray, but also all of the rays coming off of that. And you can see sort of there's a little bit of a branching factor here. Where for every point, you've got a whole number of different directions that can go. And then for each of those, there's a whole bunch of other directions. And so it's sort of trailing off into a whole bunch of light paths, and it explodes exponentially. So this is really problematic for things like real time, where you really just want to trace a couple rays, and that's all you have the performance budget for. But like we said, we've got a system, and we have to be true to that system. So suppose that we can evaluate it recursively until eventually the radiance along that ray goes to 0. So what I mean is that eventually you won't be hitting any more lights, right? If you just keep bouncing and bouncing forever, eventually you'll have done so many bounces that the new light coming in is not going to be changed, right? So let's go back to our box example to visualize this, right? Because this is a problem. If we want to do recursion, we need to have a base case, right? This is known. So let's say we're thinking about our box. We've got the light and our observer down here, and we're going to query a point, right? And then we just start bouncing. Light just starts bouncing. Now let's assume these walls are sufficiently diffuse, which means that their scattering function is even everywhere. So they just shoot out a ray randomly, right? Everything has an even value. This is equivalent to matte surfaces and materials. So once it hits here, we notice that the accumulated light increases quite a bit, right? Because now we've hit a light, and now we have that LE term to boost our value, right? Instead of just framing it in terms of everything else. But you can keep going, right? The problem is that now, once you've hit this light, the contribution from this wall here is going to be very little, because how bright does this wall have to be in order for it to have bounced across several walls, hit a light, and then the light not only emitted by that light, but also from this wall that's been carried along these paths, gets added onto the light that's emitted here. My point being that eventually you can stop simulating, right? Eventually, having that box, it doesn't make sense to go to the wall and then to the light and then to the other wall, because you've already accounted for the light that's carried directly from that other wall. So you kind of get good coverage as you evaluate enough. And typically, something like 50 bounces will be way plenty. In real time, you have to do some tricks because you can't quite do that many computations, but theoretically, you can just keep evaluating recursively until you hit some base case where things aren't changing too much. Okay. So let's pause, take some questions. How's everybody feeling? Take a look at the pretty picture. Maybe a hint at what's to come yet. Okay, so this is sort of the convergence of our path tracing now. So ray tracing is used as an umbrella term. It's also used for applications where they only trace that first ray and they don't do all the bouncing. But I'll say path tracing is the more general framework that evaluates recursively. And you can see as you take more and more samples, and this diagram has been generated by taking twice as many samples from each one over. So it is quite expensive. And down here, you're taking 65,000 samples, right, just to generate that one high quality image. Okay, any questions before I move on? Okay. All right, so now we get into the problems of this technique. Now, of course, there can't be any real problems as long as we're evaluating within that framework. You're eventually going to get the right image. But eventually is a tough word, right? And that's sort of where the barrier between mathematics and computer science gets a little fuzzy, because we actually care about how long, right? How fast, how many samples. These are the sorts of things that starts to matter more and more. So we've got these two guys. The first is bias, and this is when you're not following the system, right? This is most common as a way of reducing variance. So if you want to do a simulation faster, maybe you have this technique that violates some rules of the framework, and then it has an extra term, right? And we may or may not know what this term is, but what you're generating isn't exactly equal to the light coming out. It's the light coming out plus something. This can be positive or negative, but it's basically an over or under estimate that usually will be introduced for the sake of variance. Some of the cases in which you might know what the bias is and still want to include it instead of simply subtracting it off are things like post-processing. If you want to add like a glow to the rim of your image, obviously it's no longer going to be realistic because things don't naturally just glow around the ring of specifically where you're looking. But you can add that in nonetheless for visual effects. So that's the notion of bias. And then perhaps more importantly is variance. And this affects the rate of convergence. So I don't exactly know where this Q letter comes from. I always like to know, what that stands for or what it was originally deemed to be, but I couldn't find anything. So QN is basically our end sample estimate, is what we're calling it. And then that's the variance of this estimator square rooted will give us, this is the difference to the absolute image. So delta for difference. So this is how close are we? And it turns out that when you evaluate this, remember V is the volume of the unit sphere, so that's constant. So it's equal to the deviation with n samples, and then it scales inversely to the square root. And what that means is as you take more and more samples, the difference gets smaller and smaller. And so we might express that as saying that it converges with big O of n to the 1/2 for the computer scientists out there. And that's good. And the reason for that being so good is that other models tend to scale poorly in other terms, right? So like rasterization pipelines, for example, the thing that most video games used to be based on before ray tracing got popular. What happens is that as you have more and more triangles, it scales worse and worse, right? Things get slower. But we have this guarantee in the Monte Carlo framework that says, as long as you take more samples, it'll converge precisely at this rate. Maybe a little more, maybe a little less, up to a constant factor. But the fact is that no amount of complexity in the model space, in the materials you use, will make it converge asymptotically more differently. And then we sort of get back into that engineering mindset. Well, you say asymptotically, maybe the constant factor is really bad. And in fact, it is, right? In some cases, and we'll talk about that in just a moment, but I do want to make clear that this asymptotic convergence is a big plus. It's a big win for ray tracing. Yeah, you're definitely right in that respect. And if we have some time, I might talk about that at the end. Okay, so I'm going to declare a war on variance. I'm going to say that even if we can't reduce it asymptotically, we can still have drastically better effects, right? What I mean by that is that when we declared this estimator, right, when we said, okay, we're going to take samples, I kind of assumed that we were taking samples randomly, uniformly, in fact. So perfect randomness. You're just choosing randomly, and then eventually you'll converge. But now I've restated the problem, but with this term down here, P. And what P is the probability that you choose some sample. What I mean by that is that, let's say we have our sphere again, and we want to sample all the directions. So we might sample this direction here, right? And we might get lucky, and it turns out there might be a light source up there. So it turns out that the value of F is going to be very high with that and some other parameters, right? And that would be very good. However, if you sampled somewhere else where there wasn't a light, then this value would be very low. And it turns out that adding a very small value doesn't change anything, right? That's an important point here, right? So what you want to be doing is you always want to be sampling in the direction of the most light, right? And that's that term importance here. So when I say better sample, I mean a sample that represents
Well, Ben, we lost you. You seem to have cut out.
right? And then every now and then you can sample over here. An important sampling is the strategy we use to reduce the bias. Okay, Zoom is saying my connection is bad. Are we good?
I think we got you again.
We lost you for a minute, though.
Okay, what was the last thing that I said?
You were just about to go into the bit about sampling, more important areas.
Okay. All right, so sampling. Right, so we have this strategy of uniformly sampling, so perfect randomness of our function f, and that will eventually converge to the right result. But we know that some of those uniformly chosen samples might be useless, right? If you're sampling along the whole sphere, and say your point is sitting on like a tabletop, right, or some flat surface, any sample in this bottom half is just going to be immediately thrown away, right? Because there's no light coming through that table, right? This is known. So what you want to be doing is you want to be sampling in the direction of the most light, and that's what we call importance. Now the problem here is how do you sample in a chosen direction without messing up that nice convergence property, right? Because we say this is going to be absolutely correct to the value of the integral. So what might happen is that if you skew too many, let's say you skew all of your samples towards the nearest light, so you only sample towards the nearest light, you might be missing out on some light that's coming from some other direction, right? It's small, but it's not zero. And so in terms of that, you'll have some bias, and we don't like bias. So what we can do is we can actually divide by the probability. So if you're familiar with the statistics, this is going to come from something called a PDF. It's the probability density function, or maybe the distribution function, depending on who you ask. But this is going to tell us that the probability of choosing some point, right? And then if you adjust for that, everything is okay, right? So what that means is that instead of sampling according to the uniform distribution, I can sample according to some other distribution, and then I can adjust afterwards. And if I know that that distribution looks like F, then you achieve better results. And to convince you of this, I've got to sort of state a property of the PDF, and that's that it integrates to 1, right? So the integral of p of x dx has to be 1, right? So it's a probability density function, and this is sort of a property that we've given it to say that the probability can never be greater than 1, and the sum of all the probabilities of every sample you choose has to be 1, right? This is just a property of that function as we've defined it to say this is the measure of probability we're going to be using. And within that constrained system, you can never have, you can't always have p equal to big F, right? Because you might think that in order to converge faster, what you do is you set p equal to F, right? Because then they cancel completely and you get 1, right? But of course, if you get 1 here, then this gives you n times 1, and then you divide by n, and you get exactly 1. Well, that's no good. If we're generating 1 every time, we don't get any information coming out. So we can use that constraint. Say, okay, if p of x has to integrate to 1, and we want p to be a constant multiple, say c times f, right? So now plugging it in, you get c times f, right? And then you'll get that nice cancellation that we asked for, and this will be precisely 1 over c, right? And now the question is, what's 1 over c? Well, let's take a look over here. We'll say, okay, so now we have the integral of c times f x dx equals 1, and rearranging, yet c is 1 over the integral of f. Well, no, that's no good. We're trying to integrate f, right? So if this is a strategy to integrate f, we obviously can't choose something that has as a parameter the integral of f. We'd have no way to calculate it. So it turns out that this idealized scenario can never really work. But just know that theoretically, the best you can do is a single sample that immediately gives you the value of the integral, right? So within that, what we try to do is we try to take some probability function p that looks as much like f as possible, right? So that you get cancellation between those terms. And so let's say in a simplified graph, you get f looks something like this, right? Even if you can't match it exactly, maybe you can get p to look like this, right? And that's still better because in the areas where f is low, p is also low, which means that you're not sampling those same regions, right? All those dark areas that don't have any values, they're not quite getting sampled as much. And this is good. It's not perfect, but it's good. Right? So another issue is that big F, remember, is a product of functions, right? So we don't know. We can't just say, okay, choose p to be equal to, say, f, right? Because then you'll get cancellation in f, but you've still got this light term, and that light term might dominate in some areas, right? So what you might end up having is a distribution that looks like this, right? It's got two main regions, one that's given by F and one that's given by Li, and the whole thing is big F, right? The thing we're trying to integrate. And so what might happen is that if you sample with a probability distribution according to little p, you might get good coverage of F, but you might never be sampling these areas where Li is high. And similarly, if you have some other guy, some other p, that looks more like Li, but is low when F is high, then you don't get good coverage of F. Right, so it's sort of tricky. There's a balance to be had. Here's a reference image because I've been saying a lot of words and they may not all be familiar to you guys, and that's okay. But this is the difference between sampling completely randomly and sampling according to some known distribution. I don't know exactly what was used to generate this, but it looks like it might be according to F. So as you can see, there's a really big improvement here in terms of the samples. And remember, the reason why we care is that traditionally, if you were just using this sample over on the right, this strategy, you would have to take same number of samples. Yes, exactly. So that's the catch. You might have to take like 10,000 or more samples to get a perfectly converged image. But if these are the same number of samples, then you can imagine with this strategy, you have to take far fewer. So to get this to converge perfectly, maybe you only need 100, right? And even if that is the case, and it's probably less than 100 to be honest, you still have, 100x speedup, which in the computing world is a ton. It's huge. So even though our asymptotics haven't changed, that's still a huge speedup. And the actual evaluation, right, randomly choosing a sample according to a distribution is basically free, right? So cleverly utilizing the knowledge you have of the materials of the world in order to choose samples can actually lead to very, very crazy speedups. And this is especially important in the real-time world, where say in video games, you might only get to take 1 or 2 samples, right? So you really need to make those samples count. So now we introduce a new strategy. I say new, it's still relatively old, but an improvement onto our importance sampling called multiple importance sampling. And this allows us to sample according to a product of terms. And that's lovely because we had a product of terms, right? We had a product of F and L. So if we have a way of sampling this product effectively, will be set. And so what we do, in fact, is we sample separately. So we say, okay, take some number of samples according to this one distribution, and some other number of samples according to the other distribution. And now the catch is that we've got this weighting term down here, this W. And that's basically a way of blending the two probabilities. And this is usually some simple function balancing the two out. And it still maintains the correctness property, but there are a bunch of different heuristics you can choose for this. A common one is just to say we have NF times PF of X divided by the sum NF plus NG. Right, so you're sort of balancing these two out. And this is actually called the balance heuristic. And it's a way of making sure that you're sampling according to both distributions fairly, right? So even where one might be low, the other might be high. And this weighting term allows us to accommodate for that fact and get better coverage if we know both of the distributions. And most often we do. So here's a reference. This is a test scenario. These guys up here are actually perfect spheres that are giving off light and they don't reflect any. So you can see different sizes of spheres give off different amounts of light and in different directions. And so sampling is going to be very important, right? So sampling the light source, this is going to be sampling according to Li. You know, obviously in this column over here, you're going to get much better results when you're sampling the light source because you're going directly towards the nearest light, right? So you're going right there immediately and you're getting good results. When you're sampling according to F, you're sampling according to how light scatters across the surface. Now, there's this axis here for shininess, which means that down here, that bottom row is where it's not very shiny at all. And what that means is that the light is scattered in all directions, right? And if it's scattered in all directions, very few of them are going to be pointing at our light, right? And that's also poor sampling. But you'll see it does better when it's extremely shiny because it bounces directly, right? It shines from the viewer across that surface and immediately onto the light. And so using our new trick of multiple importance sampling, you can blend these two strategies and you can get good coverage on the left column when the light is small. And you can also get good coverage on the top row when it's very shiny and it's shining directly into the light. How do we feel about that? Sort of makes sense? And again, these are all with the same number of samples. Okay, so this is sort of where my prepared slides run out. And I said if I had some time, I'd talk about some other topics. So I'm actually going to ask you guys. I have two things that I can talk about. The first one is parallelism, and that's talking about how to exploit some hardware like the GPU, or just the fact that you're shooting a lot of rays in parallel, and we can take advantage of some computation here and there. So we could talk about that, or we could talk about real time. So this is integrating this into games. And I won't have much time for either, so I'll just take some suggestions from the chat. And if no one says anything, I'll go with the first one. Real time. Okay, we can do real time. All right, so we had this message scrolling up in the chat, the age-old technique of rendering stuff. Exactly, projecting the geometry onto the camera. So that's precisely it. So let's go back to our Cornell box. Let's say we've got our box. And there's a light on the ceiling. Okay, now the traditional way of rendering this would be to say that there's some observer here, and they're observing through some plane. And now we employ linear algebra to say, okay, take all of these shapes and do a mathematical projection. Right, that's that operation from that first year linear algebra course that you took, if you can remember how that works. So you're basically just actually projecting the shapes onto the camera. And this is great, it's really fast, and this is what GPUs were designed to do. Right, so that little chip in your computer is built for this because so many applications want to do this. The problem is that when you're projecting these triangles, you have difficulty shading them properly because you don't have that context. Right, you might not know that in world space, this guy down here, the floor, is actually being shined on by the light. And furthermore, if the floor wasn't made of a diffuse material, if it were instead made of metal, maybe it shines more in this strip here, just because of the way it's been textured or engineered, than on the other side. And you'd have a very hard time actually coming up with a good way to build that into your rasterization strategy. Because if you're just doing projections, you can maybe try to project back. But if you start sampling points on your surface, what you're going to end up doing is ray tracing, right? And that's going to be slow. So we come up with a lot of heuristics, a lot of strategies for doing realistic looking materials and styles inside of this rasterization framework. And we've gotten really good at it because this is the primary constraint, right? If everyone is doing rasterization, and there's this demand for games to be realistic, we're going to try our best to make realistic rasterization a possibility. And we've done really good. And games, even recent games, look amazing, with these pipelines. Just all these, clever hacks, tricks and tools to make things look better. But they really don't have the guarantee of correctness that ray tracing does. And now we're getting into a point in time where we can build in specialized hardware to do ray tracing quickly. So what we'll do is we'll take a ray tracing pipeline where you're rendering an image, and you'll do all the same fancy tricks, save from maybe one or two that you would normally do. And then what you'll also do, in addition to this, is you'll take a few samples by ray tracing. So not many, you won't ray trace the whole image, but you'll use some very clever sampling strategies to say, look for reflections, right? Look for caustics if there's a pool of water. Look for where the rays kind of bounce and collect up together and then shoot back either at the light or at the viewer. And this can create some really believable effects. And if you only have time for a couple samples, you really need to make them count. So this is where our sampling strategies come in. And you can get really clever with how you choose those samples, especially if you already have the image, right? Because what happens sometimes is that if you have a pipeline that's generating most of the image, and you just need to simulate the hard effects, right? The things that we can't build into rasterization. It's actually pretty simple to determine a sampling strategy. You just say, we want to do caustics, or we want to do, pretty reflection, or maybe it's shadows. Maybe shadows are hard. And so you choose whatever you're trying to do, and you sample according to that, right? So you say, okay, well, I've got a light up here, and I've got some post, and I know from my rasterization pipeline that the shadow looks like this, right? But in real life, this is actually a soft shadow. So what you'll do is you'll sample according to the soft shadow. You'll say, okay, trace just a couple rays, a few samples, and what you'll do is you'll sort of direct them, right? Because remember, this is not unbiased anymore. This is not true to our model. And so what we can do is we can just look for exactly the effects we want to use ray tracing for, and guide them into that system. And that's why even if some games may claim to incorporate real-time ray tracing, they might only be using them for a handful of specific effects. And by and large, the quality might not be that vastly increased. Okay, and I think that's all the time we have.
Thank you, Ben. That was an awesome talk. That was very, very good. Are there any other questions for Ben? Things people would like to hear more about? Ben, you're more than welcome to come back and speak again. That was an incredible talk for a first Beamer talk, and your ability to explain this stuff's really masterful. That was awesome.
Thank you. It's really fun.
On the topic of future talks, we do have a talk lined up next week. So Jesse Maltese is going to talk to us about an introduction to mathematical logic. So in the probabilistic method talk, we talked about proving Ramsey's theorem using logic. Maybe Jesse will tell us a little bit about this. But yeah, introduction to mathematical logic, a little bit less sort of applied CS than today, but there's something for everyone.
Is there a page where I could find all the future seminars and workshops?
Yeah, sure. Yeah, definitely. And if you check out that page, you'll know that we are running short on speakers. So if you haven't given a talk, you're more than welcome to. And if you have friends who are very dorky and into this sort of thing, we'd love to have them. So reach out to people you know. I'm the co-organizers, me and Lisa Jeffrey, are always looking for speakers. We really appreciate having speakers. Super duper welcoming audience. Anything is welcome. So anything that you'd like to share, please send it over to us and we'd be happy to have you as a speaker.
Is it only for undergrads?
Only undergraduate speakers or only undergraduate attendees?
Only undergraduate speakers.
I spoke a couple of weeks ago, so no, it's open.
Okay.
So I'm looking at you, faculty who are here, can see you. But yeah, anything that you'd like to share is welcome. TAs, graduate students, postdocs, faculty, anyone's welcome to speak. But please try and present something as welcoming and as friendly as Ben did today, because that was the perfect talk. That was so nice and gentle and fascinating.
All right, well, thanks for coming, everyone. I've got to drop off. This is really
Yeah.
great.
Thank you, everyone. See you next week. Bye, everyone.